Now we turn our attention to another very important type of bonding. In fact, it is responsible for the solid forms of most elements, and that's the metallic bonds. In a metallic bond, we have these metal atoms forming a solid, and you know each metal atom has one or two or maybe three loose electrons that are only loosely bound to the parent atom. So how do these metallic atoms take advantage of those loose electrons? Well, what happens is that when you put these metallic atoms together, these electrons that are loosely bound will just hop out. Of course, it takes some energy for them to hop out, but not much energy. But once they're out, they form the glue that holds the rest of the atomic structures together, because they're negatively charged, and then the ions left over by these electrons are now positively charged, and the negative positive, they attract each other. Okay, so you have all these lattice particles that are made of positive ions, but in between the lattice particles you have a sea, you have a sea of negative charges. These are the electrons that came out from the metal atoms. These are called free electrons. Free because they're not tied to individual atoms anymore. And being negative charged, they attract these ions, so that's sort of what glues everything together. This is a so-called metallic bond. Okay, now I must talk about this word free a little bit. I put it in quotation mark because when we talk about free particle, what do we really mean? We mean the free particle does not interact with anybody else. It's left alone, so therefore it's got a constant velocity, constant momentum, the force on it is zero, that sort of thing. In this sense, are these electrons moving around in what's called electron sea or electron gas, are they really free? Well, we shouldn't say so, right? Because the electrons do interact with each other, repel each other, right? And that force is what's called a Coulomb force, is a long-range force, very, very strong. We cannot quite say these electrons are free of interaction. So in this sense, they're not really free, are they? But why do we call it free electrons? Well, again, it's because they're not tied to parent atoms, but also it's because this is something more subtle. If we somehow decide to ignore the electron-electron Coulomb repulsion, okay, so we give this free its classic meaning, and that is non-interacting. And we then use that assumption of electrons not interacting with each other, and we do the calculation about the properties of this electron gas. We will in fact find a very good agreement with experiment. Now this is puzzling because after all the electrons actually interact with each other very strongly. We're not talking about say air in this room where the air molecules hardly see each other, hardly interact with each other. Electrons will repel each other very strongly. How come by ignoring the interaction between electrons we actually get a very successful approximation? Why is that? Well, let's take a look why that is the case. So we're going to focus on the electron gas or electron sea, which is formed by these free moving electrons roaming inside the metal. It's called a free electron model of metals. Again, we have to make sure free here makes sense. Free here means almost non-interacting. They do not see each other. How do we reconcile this with the long-range, strong Coulomb repulsive force between electrons? And say we can forget about that and resemble this electron with an ideal gas in which the force between molecules is truly very close to zero. How can we do that? Well, it turns out what makes things easy is actually a quantum principle. Sometimes you hate it because quantum principles make things fuzzy and difficult. But here, this quantum principle make our job really, really easy. This principle is called the Pauli exclusion principle. You remember that? The Pauli principle actually effectively turns off most of the electron-electron repulsion effectively and turns these electrons into virtually an ideal gas, which is without any electron-electron interaction. How does that work? Well, here's the thing. I'm assuming that the temperature is relatively low. Okay, does that mean the temperature has to be much lower than room temperature for the metal? No. When I say relatively low, I will qualify that later. Okay, But suppose the temperature is really low for whatever qualification, which you'll clarify later. If you have a very low temperature system and you put a bunch of particles into available energy states, clearly the priority, the overriding priority is to save energy, right? It's lower energy, right? So everybody would try to go to the lowest energy state possible, and that's fully occupied. You go to the next lowest level, and next lowest level, and next lowest level, and so on and so forth. Now, in the case of metals, okay, the metals, you can think of it as a large box, okay, it's a large box, and you throw a bunch of electrons into that box, and so we're looking at three-dimensional infinite square well. The energy levels are very, very close to each other, very, very close to each other. So the quantization is negligibly small, even though it still exists, negligibly small. And you have a whole bunch of quantum states. Okay, ground state, first excited state, very close to each other. Now, if you only have one electron in the entire box, it's going to go to the lowest energy state because the temperature is low, so that's where it wants to go. You throw another electron in there. That electron can share the lowest energy state with the first one because all they have to do is to have opposite spins. Remember, we have to satisfy the Pauli principle because these are electrons we're talking about. You cannot have the same exact quantum state. If I have a third electron, it is forced to go to the first excited state because the ground state is already occupied by both of these electrons. And you keep on adding electrons, keep on adding 3, 4, 5, 6 until you have all the electrons occupied. We're talking about maybe 1 mole, 2 moles of electrons. Where do they all end up? It turns out, since energy is very low, the temperature is very low, the electrons want to start with the lowest energy state and keep on going, occupy until the last electron found a place. Here is the last electron. It's here. Okay. Everything below that is already occupied. Otherwise, that electron would have gone down to go to lower energy state. So the electron has no other place to go below that. So this is where it ends up. Okay. It's like a hotel tower. You know, if it's a hotel tower, the cheapest room is on the first floor. The next cheapest room is on the second floor, and so on. And you have a group of people coming in. They check into the hotel, and their priority is to save money. So the first person will go to the ground floor because that's the cheapest room. And the next person will go to the first floor because the next cheapest room, and so on, until all the lower floors are occupied. And here comes the last guest. He can only go to here, maybe the 17th floor, 18th floor. But he's not going to the 19th floor because that's when it costs even more. So everything below that, all the states below that are fully occupied, and all the states above that are empty. Okay? And this is the energy level corresponds to the highest occupied state. We call it the Fermi energy. Okay? Fermi energy, EF. Fermi energy. And when an electron has Fermi energy, what kind of momentum does it have? Well, the direction of motion is still, you don't have to have necessarily move X direction, Y direction. You can move in all three possible directions. Okay? So in momentum space, what kind of momentum vector will a particle with Fermi energy have? The direction is random, but the magnitude of that K vector must be fixed because it depends on EF. So imagine you have a case where the direction is random, the magnitude is fixed. What kind of surface would that be? That would be a sphere, right? So we call it a Fermi sphere, or more generally, a Fermi surface. Fermi surface. Okay, so in a momentum space, here's the momentum space, kx, ky, kz, k is equal to kx plus ky plus kz, and h bar k equals to momentum p. Okay? Everything below the Fermi sphere, or Fermi surface, is fully occupied. Everything above it is empty. So we're looking at, really, something like this. This is part of a sphere. Okay, the surface of that sphere is the Fermi surface. Everything below that, all the states below that are occupied, all the states outside the Fermi surface is empty. Okay, and so we can talk about Fermi surface, Fermi energy, Fermi sphere, which is the shape of the Fermi surface. Assuming we can still get away with non-relativistic expression, so we assume the electrons do not move at relativistic speeds, which we'll check later, by the way. The energy of the electron inside the box is only kinetic. The only thing it cannot do is go outside the box. But within the box, we assume that these electrons are free particles. They do not interact with each other. They only have kinetic energy. P squared over 2m. P equals h bar k. And k squared equals kx squared plus ky squared plus kz squared. So again, it's a sphere. Okay, when energy equals EF, the highest occupied energy, the the wave vector k must be somewhere on that Fermi sphere. Everything below that is occupied. Everything above that is empty. And again, how does that help us address the Fermi, the interaction between electron and electron? Well, let's say, suppose I have two electrons labeled 1 and 2, and they interact with each other, so they one goes this way, one goes that way, they repel each other, so they go separate ways like that. So after the encounter, the first electron goes from initial state to a final state, 1f. Second electron goes from initial state 2i to final state 2f. That is certainly what's called a scattering event between these two electrons that's powered by their colon-colon repulsion. I want to tell you that this collision cannot really take place. Or we can say, even if it did, it doesn't make any difference to us. Why? Because, look, we just argued that everything below the Fermi energy is fully occupied. All the states are fully occupied. Everything above it is empty, or more or less empty. At least that's what happened at t equals 0. When t is very low, we find that everything here is almost occupied, everything here is almost empty. Now imagine you have these two electrons that I was talking about engaged in a collision. Where do they initially come from? Can they come from here or there? No, because there are no electrons there. It's fully, it's mostly empty. So they must both come from below the Fermi surface, right? So their energy, E1 and E2, they're both below EF. And as a result, when they collide with each other, can they have energies both above the Fermi surface? No, because that would violate conservation of energy, wouldn't it? Right? You cannot have two energies below here and then get two energies afterwards as a result. So therefore, at least one of them would have to lower its energy in order to push the other one out of the Fermi surface. Suppose this guy is originally here. It lowers the energy, pushing the other one out of the Fermi surface, but it starts from here to ends up there. Can it really go there? No, because that state is occupied by somebody else, remember? And because of the Pauli principle, somebody already has that space, you cannot occupy it anymore. Okay? So you cannot just go down in energy and push somebody out of the Fermi surface. But if you don't push him out of the Fermi surface, where does he go? This guy is not out of the Fermi surface, so he has to go somewhere else within Fermi surface, right? But remember, everything within the Fermi surface is essentially what? Occupied by somebody else already. So the Pauli principle tells you that this collision cannot take place because the final destinations, 1f and 2f, are already occupied by somebody else. You cannot do that. The only conceivable way that you can think of, which involve two particles below the Fermi surface to collide with each other meaningfully without violating the Pauli principle, is when they exchange position with each other. Okay, so particle 1 here, particle 2 there. After the collision, particle 1 assumes the state of particle 2. Particle 2 assumes the state of particle 1. So that doesn't violate the Pauli principle. And the energy is also conserved. Everything's below the Fermi surface. But guess what? That's meaningless. Okay? Then you will get the first electron become the second electron become the first electron. That's called exchange collision. Exchange collisions may mean something in classical physics because I can actually trace these electrons. Okay, oh, this green electron now went to the red spot, the red electron went to the green spot. But in quantum mechanics, that doesn't mean anything, okay? Because electrons are what's called indistinguishable, remember? So when they secretly exchange the positions, how would I know? It would have made no difference to me. They can do whatever they want. It will make no difference to me, and therefore, we say we can ignore this type of collision, and as a result, we just say no collision between these electrons below the Fermi surface. And clearly, that means that the Pauli principle, combined with conservation of energy, will render most of these collisions impossible. And therefore, we say the electron gas is essentially non-interacting. So you see, the Pauli principle really made our job a lot easier by limiting the amount of meaningful collisions to a minimum. When t equals 0, everything below the Fermi surface is 100% occupied, everything above it has zero occupancy, and therefore none of these collisions would ever take place besides the meaningless exchange collisions. Of course, t is not 0, But if T is low enough, which we'll qualify later, then the collision, meaningful collisions can take place, but they cannot take place on a large scale. In order to make our calculation of the occupation probability of any state more accurate, we should look at what's called a Fermi-Dirac distribution. This is the distribution for all fermions. We are not going to derive this distribution, but it replaces the famous Maxwell-Boltzmann distribution in the quantum case for fermions. The Maxwell-Boltzmann distribution goes like e to the negative energy over kT, right? The Boltzmann factor. Now, it is replaced by the so-called Fermi-Dirac distribution, which is valid for all fermions. Bosons satisfy different type of distribution. And here is the probability for each state to be occupied with energy E. It's 1 over the square, 1 over e to the power e minus ef over kt, and then plus 1. This is different from e to negative e over kt. You know, if you get this, then basically what you do is you just ignore this plus 1 and you flip that over, you get e to negative energy over kt, right? But this is more accurate for fermions at low temperature. So let's look at what this distribution tells us. It looks like a smooth function, and yet at t equal to 0, this becomes a function with a sharp transition. When t is very, very, very low, almost 0, but positive, okay, almost 0, then this factor here is either positive infinity or negative infinity, depending on whether e is greater than ef or e is less than ef, right? For e greater than ef, then e minus ef is positive, divided by kt, which is also positive, but almost 0. You get e to a very, very large positive number, say e to the power 1000, whatever. That is much, much greater than 1, so that 1 is gone. And then you flip that over, it's a very, very small number, so when e is greater than ef for very low t, the probability of occupancy is 0, right? 0 here, e greater than ef. But when e is less than ef, you have a very negative but large number, say e to the negative 10,000. That is almost equal to 1, okay? Almost equal to 0, right? E to the negative 10,000, for example. And so this is gone. That 1, you have to keep it. So 1 over 1, what's that? That's 100% right here. So you see, at t equal to 0, this function has 2 segments. It's equal to 1 below the Fermi level, Fermi energy, and 0 above the Fermi energy. That's exactly what we said before. Now, when t is not exactly equal to 0, let's say it's, but it's still low, okay? Then the transition is not that sharp anymore. There is a gradual transition from 1 down to 0. So stuff happens around the Fermi energy, or around the Fermi level. So you here have a little bit of empty space below the Fermi surface, and a little bit of occupied levels even above the Fermi surface. It's a little soft, the transition is a little soft. This is where collisions can take place, because I have 2 particles here and there, okay, here and there. After the collision, they can, at least one of the particles can still stay here, because these levels are not 100% occupied anymore, and that may give enough energy to another particle so it can actually move out to an unoccupied state. But the requirement is that both of these particles must have energy pretty close to the Fermi energy. They cannot be here or here. If one is here, one is there, there's no way for this guy to give enough energy to the other one to move to here. It's just not possible. Okay, so collisions will take place at finite t, not t equal to 0. It will take place, but it will not take place at nearly as frequently as classical prediction. In classical physics, all of these particles can engage in a collision with everybody else. But in quantum physics, only those electrons whose energies are close to the Fermi energy can engage in a collision with another electron whose energy is close to the Fermi energy as well. So we're looking about a small region where where the electrons will have enough energy to have a meaningful collision. That is a small fraction of all these electrons. So electrons will engage in a collision, but that collision only takes place around near the Fermi surface, and that is a small fraction of the total number of electrons. So therefore, most of the electrons are still considered non-interacting. So we still can say, to an excellent approximation, we're looking at what's called a free electron ideal gas. So this is how it works. Again, we did not derive this, but this is certainly true in our case, and we're going to use this to solve some more problems. And in our next lecture, we're going to start by finding the value of EF. EF is so important. Okay, anything below that is occupied, anything above that is unoccupied. How do we find that EF, the Fermi energy? We'll see how we can do that starting from the beginning of the next lecture.